The field of structural controls is growing rapidly. The University of Michigan is at the forefront with projects like the one PhD student Michael Kane has been working on.
What we're trying to control in a structure is we can either control acceleration, like how fast it's actually shaking at each individual floor, or we can control how much it's moved from the floor below it.
These seismic control systems use piston-like dampers to absorb some of the energy during an earthquake.
You can normally visualize it as just like a hydraulic piston. So if you kind of push on the one end of the damper, the hydraulic fluid inside is going to add a little bit of resistance to your pushing on it.
Magnetorheological, or MR dampers, use a special fluid that can be stiffened by adding an electrical current.
So the MR damper, it's not actually putting energy into the structure. The only thing it can do is remove energy from the structure. So that no matter what happens with a computer malfunction, it's kind of fail-safe. So the worst it does is go to a system as if the MR damper wasn't even there. And we can control these actuators using our Narada wireless sensing unit, which was developed at the University of Michigan. What we're hoping to do with the wireless sensors is each wireless sensor is able to sense, actuate, and it also has onboard computation, communication, and memory. So we can read in all the information, communicate it wirelessly, and then each sensor can compute what the optimal control force is for that in particular unit. The advantage of this over a central server that's doing the computation is that if that central server is knocked out, your whole system is knocked out. With a wireless network, if a single node drops out, then that node just kind of acts as if it wasn't there, but the entire network can reconfigure itself. So traditional structural control is based off of you set up a set of linear algebra and a set of matrices. You put in your sensor location, sensor information, plug it through these matrices, and then outside comes your optimal control force. Now, if your structure changes, say a node drops out or a member damages, that matrix that you're plugging things through is no longer the optimal matrix. My specific contribution to the project was developing an algorithm that would determine, knowing the displacement of the building, how much force to apply with these actuators.
The algorithm is based on economic theory, where the various components of the system are assigned some part in a supply and demand process in an attempt to be as efficient as possible.
So the supplying agent is the MR damper. The MR damper is supplying control force. The demanding buyer at that point is that structure or the displacement or whatever we're really trying to control. So there's kind of a market going on between the buyers of each individual floor and the sellers of each individual MR damper.
The testing was done at the National Center for Research on Earthquake Engineering in Taipei, Taiwan.
The shaking table is about a 20-foot by 20-foot table, if you will. It's really just at floor level that you can bolt a structure to. So we can simulate earthquakes that have been recorded in just about anywhere in the world where we can record earthquakes.
The goal of this research is to create more intelligent structural controls that are more resistant to failures, more efficient, and less costly.
So I was able to show that the wireless sensing units were able to control the MR damper, communicate wirelessly, and also execute this market-based control algorithm that was embedded ahead of time onto each individual wireless sensor to generate the control force that was desired.